In this video, we're going to go through curve calculations for heating and cooling curves. The essential question that we're going to answer is, how does energy affect the temperature and phase of a substance during heating and cooling? So some key concepts that you need to understand. If you have a heating curve, the process is endothermic. You're absorbing heat from the surroundings, and your Q, or heat, will be positive. If you are cooling, it is an exothermic process. You are releasing heat into the surroundings, and your Q will be negative. Now, when you are working with heating and cooling curves, you may be on different line segments. You'll see what I mean when we get to some examples. You want to treat each segment of a heating and cooling curve as its own problem. And again, you'll get the context when we look at an example. And finally, you should always draw a curve and label the starting and ending temperatures. So here we have a heating curve next to a cooling curve, and I've gone ahead and labeled all of the segments. So number 1, we are in a solid phase. 3, we are in the liquid phase, and 5, we are in the gas phase. Our plateaus are even numbers, so 2 and 4 on both curves are phase changes. 2, we are going to be going between solid and liquid, and then 4, we are going between liquid and gas. So for each segment, we have a different equation, but look at the equations. 1, 3, and 5 are essentially the same equation, but we're replacing the C with either the specific or the C, the C value for solid, liquid, or gas. And for our ΔH values, we are either using the fusion or vaporization, depending on which phase we're going to. All right, so let's look at an example. In this first example, it says heat 2 grams from 15 degrees to 25 degrees. So let's take a look at where this is on the graph. So we are starting at 15 degrees in the solid phase, so right here. I can't be over here at 10 joules of energy, because that would mean that I have transitioned fully into the liquid phase. So I want to start here on the left side where I am in the solid phase. And I want to go to 25 degrees here. Okay, now notice I'm on 2 different line segments. So segment 1 will be going from point A to point B. And then my second segment will be from point B to point C. So going back to what I said earlier, you want to treat each segment of a heating cooling curve as its own problem. So let's go back to our example. So for segment AB, we are going to phase change. So we have 2 grams. And we're going from solid to liquid, so we are going to be using the heat of fusion right here. So for segment AB, my equation is going to be Q equals M, heat of fusion. Okay, and let's plug in our values. So our mass here is going to be 2 grams. And our heat of fusion is 100 joules per gram. So 2 times 100 is going to give us 200 joules. Okay. Next, for segment BC, we're going to be using Q equals M C. Now we're in the liquid phase, so I want to use the C of liquid and delta T. So again, we have 2 grams. My C of liquid is 5 joules times grams over degrees Celsius. All right, and then our change in temperature. So at point B, we are at 15 degrees. And we're going to 25. So it's going to be final, which is 25, minus initial. And when I plug this into my calculator, I get 100 joules. So I want to know the total amount of energy, so I need to add these two numbers together. So I will get 300 joules as the total energy needed to go from point A to point C. So kind of like Google Maps, how to get the total mileage for your trip, it adds each street that you're on, or each road that you're on, each segment that you're on, it adds them all together to get the total distance. Okay, let's look at B. B says heat 5 grams from 30 degrees to 50 degrees. So 30 degrees is right here, and we want to go to 50 degrees, which is up here. So we are going to be on 3 different segments. So segment 1, 2, 3. So for segment 1, we are heating it to the point where it's going to start to phase change. So our equation is going to be mCΔT anytime we're changing temperatures. So I'm going to go ahead and plug in my values. So the mass that we were given in the question is 5 grams. We are in the liquid phase, so we want to use our C of liquid, which is 5 joules over grams times degrees Celsius. And then our change in temperature here. So we're going from 30 to 35, final minus initial. That's going to give you 5 degrees Celsius. And when I plug this into my calculator, I get 125 joules. All right, for segment 2, we're phase changing. So we're going from liquid to gas. So we're going to use the heat of vaporization. So we'll be using this equation right here. So I'm just going to take my mass, which is 5 grams, and I'm going to multiply it by my heat of vaporization, which is 1,000 joules per gram. 5 times 1,000 is going to be 5,000 joules. And finally, segment 3, we are going to raise the temperature of our gas from 35 to 50 degrees. So we're going to be using our C of gas here, and we'll be using our mCΔT equation again. So 5 grams. The C of gas is 1 joule over grams times degrees Celsius. And we are going from 35 to 50, so that's a change in temperature of 15 degrees. And if I plug that in my calculator, I get 75 joules. So I have my 3 temperatures, my 3 segments, and I have 3 different energies. So I'm going to go ahead and add those 3 together, and I get 5,200 joules. All right, let's move on to, let's look at this next example. Here we are heating from 5 degrees to 20 degrees. So we are starting here, and we're going up to 20 degrees, which is here. So we are going to have 3 segments. So for our first segment, we're going to be using the equation Q equals mCΔT because we're raising our temperature. So for segment 1, we're going to take our mass, which is 3.5 grams. We're going to multiply it by its specific heat value. Let's see, C. We are solid, so it is going to be 2 joules per gram. And then our change in temperature, we're going from 5 to 15, so that's a change in temperature of 10 degrees. All right, so I plug this into my calculator, and I get 70 joules. All right, segment 2, we are changing phases. We're going from solid to liquid. So I'm going to take my mass, which is 3.5, and I'm going to multiply it by the heat of fusion, which is 100. So that'll be 350 joules. And my final segment here, we are raising the temperature from 15 degrees to 20 degrees. So Q equals mCΔT, so that'll be 3.5 grams. we are in the liquid phase here, so that is going to be 5 as my C. And then my change in temperature, we're going from 15 to 20, so that's a change in temperature of 5 degrees. So I plug all this into my calculator, and I get an answer of 87.5. If I add those three up, I get 507.5 as my answer. All right, so that was a heating curve. So now let's look at an example of a cooling curve. Okay, so remember when we're doing a cooling curve, we want to use negative for our answer because we're releasing that energy. Okay, so for the first part, it says cool 2.5 grams of vapor from 100 degrees, which is here, down to liquid at 85 degrees. Okay, so I started here instead of here because I am a vapor. That second point would have been a liquid. Okay, so we have two segments here. So segment 1 and 2. So segment 1 is going to be our phase change. So for segment 1, we are going to take our mass, which is 2.5, and we're going to multiply it by the heat of vaporization, which is 20 to 60. And when I do that, I get, again, we're cooling, so it's going to be negative 5650. Segment 2, we're lowering our temperature. So since we're lowering our temperature here, it's going to be mCΔT. Our mass is 2.5 grams. 2.5 grams. Our C for liquid is going to be 4.18. We're going from 100 down to 85, so that's going to be 15 degrees. Plug this into my calculator, and I get, again, we're cooling, so it's going to be negative 156.75. And if I add these numbers together, I get negative 5806.75 joules. All right, one final example here. Again, cooling curve. We're going from 24 degrees, which is maybe around here, to negative 15, which is here. So we're going to have three segments. 1, 2, 3. All right, segment 1, we are cooling from 24 down to 0. So that's going to be a change in temperature of 24 degrees. So our mass is 35. Here we are a liquid, so 4.18. And then our change in temperature is 24 degrees. Plug that into my calculator. Again, it's a cooling curve, so this will be negative 3511.2. For the second phase, the second segment, we are going from liquid to solid. So our mass is 35. And then since we are going to a solid, that is going to be 334 because we're using the heat of fusion. That'll be negative, because we're cooling, 11,690 joules. And then our final segment, we're cooling down to negative 15. So we're going from 0 to negative 15. So our mass is 35. Here we are a solid, so that's 2.06. And then we are going from 0 down to negative 15. So here we get negative 1,081.5. Okay, so I'm going to add these three numbers together, and I get negative 16,282.7 joules. And that's how you do curve calculations.